Well, it is 10 o'clock, so let's get started. This is a big room for this few people, but that's cool. We'll make it work. Hi, I'm Dr. Obaid. Hopefully you're here for Signals 3512. If you're not, I won't say anything if you walk out. So not a lot of heavy lifting today. We're just gonna I'm gonna walk you through what this course is about. We're gonna talk about some basics, kind of like what I expect you to know, and we'll just kind of take it from there. We'll start the math in full force on Wednesday. But I just want to start by telling you a little bit about the syllabus, kind of how the class is structured, a little bit about myself. I'm going to find out who you guys are. I'm going to just call out your names just so I know who everybody is, and we'll get started. First things first, everything that I show you, I'm not handing out pieces of paper to everybody because I don't want to kill trees and I don't really want to go to a copy machine and spend my morning breathing those fumes. So this is all on Blackboard. You can never lose it because it's on Blackboard. If you can't see our course on Blackboard, come talk to me. We'll sort it out. All right. But everything's on Blackboard. And that's probably the first thing that you should know is that, that's kind of be like the main way that we kind of get information back and forth. So this is Signals. Signals required course. Mostly juniors take this. Basically it's, I like to think of it as the mathematical theory of information, right? We're actually, you can think of it like another math class. So what I like to tell folks is that, like, why are you studying electrical engineering, right? Why do you bother learning about circuits? And why do you bother, like, studying computers and what have you? And the answer is that electronic circuits and computers are like the best way we have of manipulating and storing and communicating information, right? Like if you have an MP3 file, that's information, right? That music is information that's been stored and you can play it back when you want to. If you want to write an email message, if you want to take a picture, okay, that's all information, and that's rebuilt circuits to handle that kind of. I didn't turn the mic on yet. I'm sorry.
Oh, it's already on.
Oh, it's already on. Oh, great. Okay, great. I just need to clip it on myself. Okay. Sorry. Feel free to tell me next time. Yeah, we're gonna podcast all this. If in fact engineering is all about information, then you need to study the theory of information, right? You need to understand what is information. How much information can you store in a signal? What is a signal? What's bandwidth, right? What limits how much information you can transfer within a given amount of time, right? What limits the fidelity of a photo that you can take with a certain circuit, right? So that's the theory of information, and that's what you're going to learn in Signals, okay? The theory of information. And basically, it's just a bunch of math. We'll do a few circuits here and there, but at the end of the day, it's mostly math. So anyway, that's me. I have an office on the 7th floor. Don't look for me there. I never go there. I basically just use it for storage, and if I have to meet with somebody important, I unlock it and clean the desk a little bit. Basically, I'm in my lab, room 215. That's where I'll hold my office hours. Wednesdays and Tuesdays. Yeah. Would have made more sense to put Tuesdays first, whatever. Tuesdays and Wednesdays in the afternoon, pop on in and see me. If you're really desperate, I try to hang out on Skype, more than Google Talk, but feel free to just contact request me. And I've done a bunch of office hours by video chat before, like from home at 1 in the morning before a final exam. It works really well. So don't be shy. Like if I'm hanging out on Skype, that means it's okay to hit me with a question. If I'm busy, I just won't answer you. So like no harm in trying. We have our TA, John. That's John back there. This is about the 83rd time John has TA'd this class. He knows the material better than me. He is going to be running your recitation. So that's probably the first thing we should talk about. This class comes with a recitation. You have to be registered. Are they Mondays and Wednesdays? Is that the deal?
Yep. 1 to 150.
1 to 150 on either Monday or Wednesday. You have to register for it. And then you have to go to it. John, how often do they need to go?
Once a week.
Every week. Every stinking week. Recitations are, yes.
Does that include this week?
That does not include this week.
Okay.
So not really every stinking week, but close to it. So the thing with recitations is they are an integral part of the class. You can't blow them off. If you blow them off, your grade will suffer. Your grade will suffer in two ways. One is that 10% of your grade is going to be based on whether you show up to recitation and participate. Number two is you just won't learn the material. So go to recitation and participate, okay? There'll be basically, you can think of it like, I'm going to hand out a bunch of recitation problems. And recitation is just going to be a chance to work through those problems. There will always be a pre-problem, which is something you have to complete before you arrive to recitation. That's so that you come prepared. Do the problem. You'll get graded on the problem. Read the rest of the problems, right? It'll be a waste of your hour if the first thing if you're spending the hour like looking at those problems for the first time. So it wouldn't kill you to spend an hour at home looking at those problems, trying to work through them. Even if you don't know how to do them, at least you know what it is that you don't know, right? So that's valuable. So come prepared to recitation. Prerequisites. Circuits 2, Calc 3, C- or better. No exceptions. If you don't meet those requirements, unfortunately you're going to have to wait till another term to take this class. Unless there's some sort of like weird, freakish, standout circumstance, in which case you can talk to me. Textbook. You don't have to buy a book. So that's like one of the things that I've added to this class. When I started teaching it, there was a book. People did not like the book. It was expensive, so I wrote my own book, which I somehow forgotten to put on Blackboard. So I will put it on Blackboard. But basically, it looks like this. Did I even put this? Basically, it's organized by lecture, or at least it was organized by a lecturer for the semester when I wrote it. So, you know, for any particular lecture, you open it up. You know, it's maybe like 4 or 5 pages for each lecture. The book is not optional. You have to read the book. There's a lot of good stuff in the book. It underscores a lot of the things we talk about in class. It'll save you from like taking a bunch of lousy notes. I mean, you should still take notes, but you know, it's kind of well organized and well thought out. I put a lot of time into it. Please read it. Like I didn't do it for fun. I mean, it was kind of fun, but not that fun. So read the book, and you know, try to stay up to date with it. This is the old book that we used to use. Like, if you really feel the need. I mean, it's not. I didn't think it was a bad book. I was kind of surprised when students started complaining about it. But it's a pretty good book. It's kind of a standard. If you feel the need for like something on your bookshelf or like another source of information, I can endorse the old textbook. So there it is. It's in your syllabus. All right, let's have a look here. We're going to be using a lot of MATLAB. And if MATLAB scares you, there's this great book called Getting Started with MATLAB 7. It's about this thick. It's in paperback. You can buy it brand new for about $30. It is the best. It's no frills. It's just like, this is the basics. This is how you make plots. This is how information is. So if you feel the need for a book that explains MATLAB, that's a great bargain. Okay, so this is sort of like the crux of it. This is where I get to right here. Ultimately, it's your responsibility to learn signals. It's not my responsibility to teach it to you. It's your responsibility to learn it. My teaching style may not fit with the way you learn. That's unfortunate. I try to be very accommodating, but the reality is like everybody learns differently, and every instructor teaches differently. This is not the only place in the universe where signals is taught, right? It's been taught in like every university in the world for like the last 50 years. There's a lot of material out there. There's a lot of stuff on YouTube. There's a lot of like books. There's a lot of stuff that people have written. If whatever here is not working for you, it's kind of like your responsibility to find something that does work for you. In fact, like easily like once a year, I learn some new signal processing technique that I didn't know about before, and I just sort of teach myself about it by poking around online. Like somebody will have posted a YouTube video, or there's a PDF online, and like I read it and I learn. And if I don't like the first one, I try the next one. So there's a lot of good stuff out there, right? Like, don't be afraid to go and look. I mean, this lousy little book that I wrote is not the end all be all. So anyway, poke around. There's a lot of good stuff out there. Find something that works for you. Okay, so there's the stuff we're going to work on. Fourier. You guys learned Laplace transforms? Yeah, okay. So Fourier transform is basically like a subset of Laplace transforms. They're closely related, but we're going to be looking at them from like a slightly different perspective than what you would have learned in Circuits 2. But essentially, whatever. I mean, we'll get into all that later, but that's in case you care. That's the list of materials or the list of subjects. Now look at this. I'm organized now. I didn't used to do this. This is it. This is like your whole timetable for the semester, okay? You don't have to say, when's my first exam? When's my homework due? That's it. Everything is written in stone. So the way this works, we're going to have 2 exams and a final on those dates. Your final's at 8 in the morning. I hope you're early risers. I don't set that time. The university does. I'm as unexcited about it as you are. So anyway, we're going to have 2 exams and a final. And then the only homework we have, we're not going to do weekly homeworks. I've never cared for weekly homeworks. Plus you have the recitation, and the recitation kind of serves as your weekly, just practicing doing equations kind of thing. Instead, what we do is we're going to have these 5 computer assignments. And what the computer assignments are kind of like open-ended problems that you're going to solve. And it's the kind of thing where like there's no one right way to do it. You kind of have to think about it. You'll have to write some MATLAB code. They're tricky, right? They're not clean. So you have to do the problem, and then you have to write up a little lab report saying what you did and kind of arguing why you think you understand what happened and so on and so forth. So you'll get about 2 weeks. In each case, you're going to get the assignment handed out at least 2 weeks in advance of when it's due. So you'll have at least 2 weeks. Hopefully more, but in every case you'll have at least 2 weeks to do the assignment. You'll be able to work in groups of 2, and usually they're pretty good experiences. Like I'm adding a new one this year where I'm going to give you a sound file that's got the sound of a phone being dialed. Like when you dial a phone, you hear the tones. You have to decode the phone number from the tones, right? So it's that kind of thing. Like there's a lot of ways to do it. But ultimately, I'll teach you. I mean, it's cool, right? You're going to learn. So anyway, it's that kind of thing. It's open-ended. Like you have to think a little bit. It's not just like cranking some numbers through an equation and hoping for the best. We'll talk a lot more about those. I will tell you exactly how I want your lab reports prepared. That's like a whole thing that we're going to do. MATLAB. Is everybody okay with MATLAB? Never used it. Okay. So I get that a lot. We're going to have MATLAB coming out of our ears this term. So the first thing you need to do, if you have a personal computer, a laptop, something at home, you get to get MATLAB for free. The university has picked up the tab for it. For free. All you need is an email address that ends in temple.edu. And you get MATLAB for free along with 50 toolboxes. So the way it works is there's a core MATLAB engine. And then there's all these extra toolboxes that have added functionality, which you can pay extra for. So Temple has bought the main engine plus 50 toolboxes, which is like a $7,000 bargain. And you get to download it for free. Okay. Plus, it's on every computer in the university. So the way it's going to work is I will do a bunch of MATLAB code on the computer. All the code that I write, I will post. You'll do MATLAB code in Recitation. We'll have some lectures which are basically just devoted to MATLAB literacy. But you're also going to have to take some initiative to learn it yourself. I'm going to post on Blackboard. There's some like good little tutorials to get you started. But like I was saying a few slides ago, there's a ton of stuff out there for you to find this on your own. So, I'll help you, but you got to take some initiative yourself if you're not MATLAB friendly. But don't worry, by the end of the term, everyone's going to be a MATLAB ninja. And it's good. It's like really an industry standard tool. Okay, so here's your grading. Recitation, 10%. Show up, make your voice heard, do problems at the board, ask questions. You'll get your 10%. Okay? Don't show up, sit in the back, don't answer questions, don't come prepared, don't act surprised when your grade sucks. So the computer assignments, there'll be 5 of them. The 2 exams and the final, each worth 20%. And then we're going to have weekly quizzes. Those will be worth 10%. Technically, the quizzes will be unannounced, but you can expect them once a week on average. And basically what's going to happen is at the end of class, I'll give you a quiz. It'll take 5 minutes. If you've been keeping up with the material, quizzes will be a snap, or they shouldn't be too hard. If you're 3-4 lectures behind, if you haven't been paying attention, you're going to lose those points quickly. It's 10%. In my experience, that's like one of the most overlooked ways that people throw away their grade. They don't come to lecture, and therefore they can't take the quiz, and that gets you a 0. Or you're just not paying attention, and you didn't come to office hours because you got behind or whatever, and you're going to get a 0 on a quiz where you should have gotten a 5. So those make a difference. So please, come to class. Let's see. Other than that, this is the rest of the syllabus is just crap they make me put in there, because I work at Temple, and it's just required. But I'm a nice guy. If you have a problem, come talk to me. If something's confusing or boring or whatever, just come talk to me. Okay, questions.
So you don't do makeup quizzes then?
If you had like a really good excuse, if you don't have a good excuse, you're just not, there's no makeup. But if you were really sick or like your dog got run over or something, I mean, we can work something out. But if you just, if it was like traffic or something, or I didn't get out of bed or whatever, like, no. So there you go. All right. That's a good question. Thank you for asking. All right. Anything else? All right. I'm just going to, yeah?
MATLAB compatible with Linux?
Yes, MATLAB works on everything. MATLAB is Mac, PC, Linux. You can go back and forth between them. I mean, like I use Dropbox. I have some machines running, Windows, some running Mac OS. Like, it just works. It's all.
What license do we get?
What's that?
Can I run on the laptop and the desktop?
Yeah. I've got it installed on like, I don't know, 8, 9 machines. Yeah.
Normally they're restricted by license.
They don't care. Temple just, whatever it is, they wrote a big check and you can do whatever you want. I mean, as long as you've got, literally like using my username, I have it installed on this machine, the one in my lab, the one in my 2 in my house, and maybe like 3 that my students use. I mean, I'm literally like, I'm running 8 copies of it and no one seems to care. So knock yourself out. Okay, I'm going to find out who's here. And please just tell me how you want me to say your name, right? I mean, don't make me sit around for a whole semester calling you something you'd rather not be called. Okay, Robert. Okay. Hussein. How you doing? Nobody gets it right? Got your back. Andrew. Geed. Oh, he said he wasn't coming today. Yeah. We should have a quiz. Cedric. Cedric, how you doing? Daniel. All right. Oh, I've got 2 Daniels. Do I have 2 Daniels? Eureko?
Yeah.
That's you. Okay, so that's Daniel. Daniel, Dan? Dan. Okay. Kofi? No Kofi. Gesner? No Gesner. You're here. Rhett?
Here.
Right, okay. Brandon? How you doing? Dan Coe. Dan or Daniel? Dan, 2 Dans. Okay, thanks. Joseph? How you doing? Joe, Joseph, don't care? Okay. Peter? Pete's fine. Pete works for me. Sammer? Sammer, all right. What's that? Sammer? My brother's name is Sammer. So there you go. Of course, hello.
He goes by Sammy, though.
He goes by Sammy? I'm calling him Sammer.
Only on the streets, right?
Pascal? How you doing? Jesse? Rougeau? No. Eric? I got Eric. Abu is not taking it. Randeep? Not taking it. Brian.
Here.
Two Brians.
Ron.
I got Thibodeau.
Yes.
Is that you?
That's me.
Okay. I've got you, Brian.
Ryan.
Ryan. Oh, did you just register?
Last week, yeah.
You're not on this list. Okay. Okay. Let's touch base after class. Is there anyone I didn't call? I didn't call you. You're not. Okay. I didn't call you, did I? Okay. So we got like 4 I didn't call. Go Temple. So let's just do this. Come and see me after class instead of like me trying to search all this now. We'll get it worked out. Help me out with your names. I'm really going to try to learn everyone's names. It's just going to take me a few hacks at it. But we'll get it. Okay? All right. Questions?
For the computer project,
Yes.
we can be working in groups of 2.
Yes.
Like my partner is going to be the same for the whole project, the whole semester, or?
No. Actually, usually what happens is people start working in groups, and then they decide they hate each other, and then they start working by each other. Like, it's fine. I don't care. It happens every semester. Like, people make these, like, yeah, it's going to be awesome, and then, I can't stand my partner. So, like, just, okay, don't work with him anymore. Whatever. No, you're not, there you go. Yeah.
Like if you're working with a partner, like you can have the same code, but the reports have to be individual.
No, you're handing in one report.
Oh, one report.
Yeah, do you want me to have to grade more stuff than I need to?
No.
No, right? That's what I'm
Works out
thinking.
for both of us.
Right, it does. No, and there's a reason for that. Like, I kind of thought it over. One, it cuts down on the workload a little bit, especially like there have been semesters in the past where I've had 60 students in this class. And, I can barely grade them fast enough as it is. So letting people work in groups of 2 halves my grading. But I think it's actually also a good experience because watching people fight over writing a lab report is hilarious. And you think like you're going to have like real jobs in a couple of years. And I mean, if you can't handle this, you got problems. So it's a good experience. And people divide up the labor like however works for them. Some folks, some folks are like one person will write the code and one person will write up the report. I don't know, whatever works for you. However, you are responsible for knowing what's in the report. So typically what will happen is on your exam, there might be problems related to the computer assignment. And if you didn't understand the computer assignment, you can expect to take a 0 on that problem on the exam. So that's kind of like my check just to make sure that you didn't just hand in something that you didn't understand, right? So you both have to understand whatever's handed in. But, pick someone you like. Or don't pick anyone at all. Like, I really don't care. If you want to work by yourself, that's fine too. People work by themselves every semester. Okay. So we're going to go through this little exercise. I like to do this at the beginning of every term. And we're going to basically just kind of talk about what's a signal and what's a system. That's awesome. Looks like somebody didn't erase this all summer. And now we're going to have to look at it. 30 minutes left. Each. Okay, whatever.
People bring in permanent markers and then
Right. Well, actually, I found even with a dry erase, like sometimes in my lab, we'll leave dry erase on the board for like 6 months, and then, you need a new board at that point. Even with the chemicals, I can't get it off. But anyway, so it's right in the middle. And it looks like my markers dried out over the summer. So we're going to talk about signals, and we're going to talk about systems, right? That's the name of the game this term. So signals is kind of like information. And systems is like acts on information. So let's brainstorm. Let's get a little bit creative. What's an example of a signal?
G-code.
What's that?
G-code. That qualified signal. G-code. What goes across?
G-code?
Yeah.
What's G-code?
For CNCs.
Oh, okay. That sounds good. I've not heard of that. G-code?
Yeah.
Okay. What's that?
Basically, it tells the router or whatever you got working what to do, like left, right, up, down, how many spaces.
Oh, like for the CNC machine?
Yeah.
Okay, yeah. Yeah, absolutely. That's a cool one. No one's called that one out yet. So a CNC machine is, what is it?
Computer numeric control.
There you go. Like, I can never remember what it stands for. It's basically they're machines that will either like plot or etch or make circuit boards, but you have like a thing and then you've got usually like a drill or an etcher that kind of goes back and forth over it and carves it out or what have you. So apparently you have G code to organize that. There you go. That's swinging for the fences. I like that. All right. A few more examples.
Radio frequency.
Just how about radio signals? I don't want to pollute with frequencies yet. We'll get to frequencies. Yeah, but radio. You turn on your radio, you're listening to a signal. In fact, I'll go do you one better. How about anything that's audio? Right? I mean, even when I'm speaking to you now, my voice is a signal, right? Is it conveying information to you? I hope so. I mean, but yeah. So any kind of audio is a signal. What else you got?
Semaphore.
Semaphore. You mean like the ones on a boat or the ones on in like real-time operating systems?
One's on a boat.
There you go. You guys ever seen these on a boat? You know, you got a boat, you know, and you got those the flags on the boat, you know, with the, I don't know, whatever they are. Those are called semaphores, right? So you can send signals from one boat to another. Okay? So if you got a boat like a mile away and you need to tell it, I don't know, something, you hold up the flags and the guy can see the flags and he knows what you're talking about. Yeah, absolutely. That's a signal. Any other ones?
Infrared remote control.
Ooh, there you go. Infrared remote. Yeah. How about a Bluetooth remote, right? Anything that's Bluetooth. That's a signal.
NFC.
What's
NFC.
NFC? What is NFC?
Near field
Near field.
communication.
Oh yeah. You guys are getting good ones. Near field. So some of these are like methods of communication and some are actual signals. So like audio is a signal. You know, like visual stuff. Video is a signal, right? Like anything that's visual is a signal. What if, let me give you some other examples. What if I gave you a list of stock prices for some stock over the last 6 months? Is that a signal? It's information, right? Yeah, I like that one. Stock prices, okay. You know, what if you, yeah.
What about the sensors? Like, can we use the information in the sensor as a signal to use as forecasting, like the stock prices?
How do you mean?
Like with stock prices, you said whatever information I have for the last 6 months,
Mhm.
you can use it as a signal to use forecast for what's happening to the market.
Right. So that's when we talk about systems, we'll talk about that. Forecast. Right. That's the next part of it. That's absolutely right. So let me add a couple more here just to kind of get you thinking. You know, what about, you know, what if we just put some, like a weather station outside on the roof, right, that measured like temperature and humidity or like barometric pressure? That's a signal, right? Any kind of weather data. Those are all just, I'm just trying to like make you think that like there's all this stuff out there that's just information. It's signals. But ultimately, it all has like a bunch of things in common, okay? And usually, what I like to think of it is that if it's information, that means you can plot it. So for example, you know, if we were looking at stock prices, you know, you should be able to plot it, let's say, versus time. Okay, there's a stock that's not doing too hot. Okay, but the point is that usually signals can be, it's like representing some sort of information, and usually there's an axis. Okay. Usually there's an axis. Sorry, let me rephrase that. Usually there's just a pair of axes. I'll clarify what I mean by that. But you know, if I drew you an audio signal, it would be some signal versus time, right? Where there would just be like wiggles according to what your voice sounds like. So on and so forth. So what about visual? Like what if I made a movie, let's say? How many axes? How am I going to plot that? Can I plot that signal? How do I do that? Yeah, I need 2 signals. Actually, I need a lot more than 2 signals. But in theory, like, so this could be, we said, either stock prices or audio, but basically it can be plotted. But what about, so now my example is, what about video signals? So if you look at an image, like your standard 2-dimensional image has 2 axes, right? If you look at an image, like if you take a picture with your phone, it's got a bunch of pixels, right? So, you know, some pixels might be dark and some pixels might be light and then so on and so forth, but it makes an image. So now you've got an x-axis and a y-axis. And then if you want to make a movie, now you need time, right? So now you need, like, I don't know how I'm going to draw that. But then you get to time. So there's always, you can always think of signals as basically being versus time if they're changing. Okay? So that's how I like to think about signals. You can usually plot them in this fashion. Now, what is going to take up most of our time for like the first half of the class is we need to change how we think about plotting information. So up until now, the most common way, like if I gave you stock prices and I said plot them, the most natural thing to do would be to plot versus time. You with me? Yeah. That is going to end. Okay? Time is fine and time is useful because it's very natural and we live in a world that goes versus time. But we are going to change our thinking, and instead of plotting versus time, we're going to think about taking the same information. I'm sorry, I will show up with better markers on Wednesday. We are going to start thinking about things as being versus frequency. All right? So, it turns out, and we'll explain all this in a lot more detail, but it turns out that, let's say we look at this stock plot that I've given you. You can think of this stock plot as containing some information. Okay? There's a theory, which we will study and beat to a pulp, that states that all this information, that exact same knowledge, can be expressed, instead of by plotting it versus time, you can plot that same information versus frequency. So this might contain some high frequency components and some low frequency components, and you could just plot that. You could say, well, there was some stuff at low frequencies and some stuff at medium frequencies and so on. And it turns out if you do it properly, you can say all the same stuff, you can convey all the same information either with a time plot or a frequency plot. And it turns out the frequency plot is a heck of a lot handier for some things than the time plot. So we'll kind of learn to go back and forth between the two. That's a major part of what we're going to do this semester. I'll give you one example right off the bat. Okay, then I'll get away from this and we'll talk about systems and then we'll kind of call it a day a little early. What if I drew, I'm going to draw a cosine for you. Does everybody remember frequencies, cosines, how to do that? You're going to get real good at it real fast. Yeah, I'm seeing a wiggle. Okay, we need a marker that does not suck. What about this one? Sometimes a kind soul leaves one out for the instructor. Oh yeah. There's another one here. Bear with me, we'll get through this. All right. Let's try this one. No, so that sucks. That sucks. That sucks. That sucks. Well, if you wanted good markers, you should have gone to Drexel. Yes? Oh, almost at it. If you wanted an instructor who could catch markers. I usually don't use the Drexel joke till later in the semester, but you know. Hey, all right. Okay, so, whatever. So, here is this a sine or a cosine? It's a trick question. They're the same thing. The only difference between sine and cosine is a little phase shift, right? Basically, I want you to forget about sines. A sine is just a cosine with a little phase shift, okay? And it's not going to do us much good to think about sines and cosines. So whatever. It's a cosine and a sine. It's all the same thing. Okay, so here's a cosine. And I want you to assume that it goes on forever. So I would keep drawing squiggles till my arm fell off in either direction. Okay, so what is the period of this signal? 0.1 feet? Seconds. Okay, so the period is 0.1 seconds. Great. What is the frequency of this signal? What are the units of frequency? Let's start with that. Or, there are 2 units of frequency. Okay, and unfortunately they're confusing. And unfortunately we need to make friends with both of them. I'm sorry. That's how it is. I didn't make this up. Okay, there are 2 units of frequency. The first unit of frequency is hertz. Okay, so the relationship between hertz, between frequency and the period, is that they're just the reciprocal. So in this case, it's 10 hertz. And this makes sense. Like, if it takes 1/10 of a second to do one period, then in 1 second, how many times will this signal go up and down? 10 times, right? If I waited till 10 seconds, sorry, if I waited for 1 second, I would see that this signal had cycled 10 times. So there you go. That's what 10 means. 10 hertz, 10 cycles per second, right? That's a hertz is cycles per second. Now the other unit of frequency is radians per second. Oh. So let me draw a circle. Bless you. So he said a hertz is a cycle, right? Cycle per second. So if you have a circle, how many radians does it take to go around a circle? 2 pi. Look at you guys. So if I start here at 0, I go all the way around. That's 2 pi radians. So tell me, if in 1 second I do 10 cycles, how many radians do I do? So in 1 second, I'm going to do, right, in 1 second, I'm going to do 10 cycles. Let's count the number of radians that I did during that time. So here's my first cycle. How many radians? 2 pi, right? My first cycle, 2 pi. My second cycle, 4 pi. 6, and so on and so forth. So if in 1 second I did 10 cycles, how many radians is that? For each cycle, I get 2 pi radians. So my frequency is 2 pi times my frequency in hertz. So in other words, 2 pi times 10 is 20 pi radians per second. Those are equivalent. If I tell you 10 hertz, you immediately know that I'm also talking about 20 pi rads per second. And vice versa. If I tell you the frequency is 20 pi rads per second, you know that I mean 10 hertz. Now, here's what I meant about representing information on either the time axis or the frequency axis. What if I came and I drew you this picture? I'm going to draw you an axis. And over here, instead of labeling it time, I'm going to label it frequency. So, does this signal have any information at 0 hertz? No. Does it have any information at 1 hertz? This signal only contains energy at 1 frequency. So, here's what I'm going to do. 10. I'm going to put a little stick there. We'll get into the math behind what's in the stick later on. Okay, I mean, it's actually an impulse, and there's a whole lot of math that goes into describing that little pokey stick. But it's a stick. Okay, and that's it. I'm done. And I'll describe how, what's on the y-axis later on, too. But can you agree with me that here I'm describing a signal that only has energy at 10 hertz? And here I'm describing a signal that only has energy at 10 hertz. So would you agree with me that even though this plot is versus time and this plot is versus frequency, they're telling me exactly the same thing? That's all I'm trying to say. Yes?
What about the wave like before 0.1, like the rest of the cosine wave?
Well, but that's what this is. It goes on forever. This is a cosine.
You're only plotting at 0.1?
No, I only plotted it from 0 out to like 0.2 just because I don't want to draw for infinity. I mean, I'll run out of board. But this, I want you to assume that this signal is infinitely long. And that entire infinitely long signal is a single cosine that repeats itself at frequency 10 hertz. So these guys are totally equivalent. Yes?
But what if it doesn't repeat itself like that?
That's why you have to take this class. Because this one we can do by, seriously, this one you can do by inspection. Okay, the question is what happens when it doesn't repeat itself, or it's not infinite duration, or it changes, right? Or it's like an audio signal then you need more sophisticated tools, and that's what we're going to study this term. But I'm just trying to illustrate the general concept. But yeah, that's exactly right. Then you need some better math. Yes.
What would the unit for the vertical axis of that frequency be?
It's actually complicated. It's sort of it's unitless, believe it or not. And actually, if you care to know, there are going to be 2 axes. We have to make 2 of these plots. There's a magnitude plot and a phase plot because this turns out to be a complex expression. But we'll get there. Yes.
So but your units are going to be the same for the vertical axis.
As for no, absolutely not. No, because this could be volts, right? It could be volts. It could be like sound wave levels.
Would there be a volt there for frequency?
I'm sorry?
So you would change the units when you go to frequency?
No, the units in the frequency domain, the units are always the same. It's just magnitude and phase.
Okay.
Don't worry too much about the units. I want you to see the big picture. I don't want you to lose yourself in the details yet. I'm just trying to make the point that it's the same information in both plots. We'll, in the time domain, the units depends on whatever the signal is. In the frequency domain, it's always just, you have 2 plots. One which is magnitude, which is technically unitless, and the other one which is phase, and I'll describe all this later, and its units is in radians. Yes?
So if you have a stick going up for 10 hertz,
Yeah.
would you have a stick going down at, let's just say, 0.05 or 5 hertz?
And for this plot?
Yeah.
Is there any stuff at 5 hertz?
Well, it's the same thing, just downwards. Right?
Where, you mean here?
Yeah.
No. There's no, this, so this is great. You mean because right here it's 0.05? Is that kind of what you're saying?
Yeah.
Right, but that's not what's happening here, right? Like if I were to write an expression for this signal, it would be cosine of, we always write cosines as 2 pi 10 hertz, t. Right, for all time.
Okay.
So essentially all I'm doing is I'm saying this is a signal with frequency 10 hertz. Of course there's going to be some stuff at 0.05 and a 0.15 and a 0.2, but overall it's a cosine with that frequency.
So you only care about the positive peak?
Well, you just care about how frequently it repeats itself. I mean, you can count the negative peaks. Like, this is 0.05, this is 0.15. So how long is it? So the frequency is, the period is how long it takes for the signal to repeat itself. So how long does it take to repeat itself? 0.1 seconds.
Care about the period, you don't really care.
You just care about the period, right? It doesn't matter where you start, where you measure from. It's just how long does it take to start repeating itself? 1/10 of a second. That's all that matters. Now, just as equivalently, instead of plotting this versus hertz, I could have plotted this versus rads per second. And what do I have to change? Right. That 10 becomes a 20 pi. Same thing.
Does that go down to negative? Does it go to positive and negative infinity? Or is it just positive for the frequency?
Oh, the frequency?
Yeah.
Frequency can go all the way to positive infinity. And we'll get to that. Like, it's one of these things where, mathematically speaking, we can talk about infinite frequencies. And mathematically they exist, and mathematically we need them in order to make certain problems work out. Realistically, good luck with that. I mean, at some point, like real-world limitations kind of, you can't really generate infinite frequencies and you can't measure them, but kind of mathematically they're there and you need them to kind of make the math work out. But you'll kind of see reasonably sooner or later that kind of what the limitations are. And believe it or not, there are negative frequencies as well. We'll talk about that too. That's what really gets nutty, is that this axis also goes in that direction. That's where it gets ugly. But okay, I'm not trying to scare you. I'm just trying to like get you ready to think about signals. Okay, and it's all basically a study of cosines. Okay, quickly before our time is up, we've got about 3 or 4 minutes left. Let's just talk about what's a system. Let's talk about some like really common systems. Computer, circuit. Anybody got an iPod? Right? iPod acts on information, right? You feed it an audio signal, it amplifies it, it plays it for you. Sure, right? A vending machine, that's funny. A vending machine has got a circuit in it, and that circuit does things like count your money. It's got a finite state machine that takes your input. Basically, I would describe a system. There's generally reasons why we want to act on information. Like one reason is we want to make predictions. Okay, and that's probably the biggest one. Like if you think about radar, like radar is such a common example because there's a lot of history kind of tied up into engineers inventing radar and so on. But like if you're flying an airplane and you want to know how far it is to the ground, you send a radar signal, okay? And the radar signal bounces off the ground and it comes back and you measure the time of flight and then you make some sort of prediction about how far you are off the ground. So the signal is the radar signal, and then the system is the thing that processes it to make a prediction. How high am I off the ground, or how far is it to my target? So systems basically let you make predictions. If you're talking about stock prices, right? The big thing now is that people write computer algorithms to predict when to buy and sell stocks, right? Wouldn't it be nice if you could use your knowledge of signals to make predictions? This stock is a good value. We should buy it. It's going to go up. This stock is a bad value. You should sell it. That price is going to go down. And I know that because I've taken the signal, right, the past 6 months of stock prices, and I've analyzed it in a frequency domain or whatever, and I've made a prediction that almost certainly it's going to go up. Yes?
Isn't the stocks more or less like random signal?
Oh, well.
Well, some people say
There-
it's got random inputs, but
I mean, there's a whole can of worms behind that. I would say that it's not random, but it is like you might find that some stocks are correlated, right? So you could study one technology stock and it does some action, like it goes up, and you might deduce from that that it's more likely that this other stock is also going to go up because it's related, for example. Well, I can tell you for a fact it's not random because I know that people make tons of money predicting stock prices with computer algorithms.
I would predict probably within a certain time frame it is more like random, but over a longer time frame it is more controlled. So
There's an element. That's why you take the next class. The one after this is called stochastics, which basically takes all the stuff we're going to learn this term and combines it with the study of randomness. So the thing is with like randomness doesn't just mean totally unpredictable. Random just means like you may not be able to predict exactly the next event, but like you're saying, on the whole, like if you waited for, if you looked at a bunch of measurements, there would be definitely some pattern there, and you can exploit that pattern. Okay, we'll do this in more detail. This was just kind of like to get started. If you could start by reading the first 2 lectures, which I'll post on Blackboard today, and make sure, like, your first quiz is going to be something like, what is the frequency of this signal? Okay, and I'll give you a cosine, and that's it, right? It'll be something in that neighborhood. But make sure you can do like simple stuff like plot a cosine, or if I gave you a cosine, you can plot it. We'll practice that on Wednesday, but make sure that like don't look at me like it's the first time you've seen it.